Right. So as I was saying, yes. Yes, so they were studying the classical elements and studying different substances. And you know, the idea of elements was way before these times, right? The idea was that nature, all the substances in nature, is made up of substance, well, are made up of simpler substances. And so everything that you see in nature are actually made up of simpler substances. And these simpler substances combine in different ways to give you the materials that you see. So, like, well, obviously, like, okay, some examples that they would use would be art. I'll tell you that just now. But the classical elements, so they figured that, okay, everything was made from earth, water, fire, and, well, earth, water, air, and fire, right? And the different things in nature were various combinations of these. Were, well, simple things you would understand, like mud, obviously, that's earth and water. But then you have things like wood, which is another combination of earth and water. And I guess the reason that being that plants, absorb nutrients from the soil and absorb water from the soil as well. They figured, wood was another combination of earth and water. Your breath was a combination of fire and air because it, got hot. Things like that. So they figured that, okay, these were the simple elements, and okay, these things, if these are the elements, then literally elemental means basic, right? That's why elementary school is there. It's the most basic school. It's where you learn your fundamentals. So these substances are supposed to be the most basic substances, and um, they aren't supposed to be, if one thing is an element, then it's a simple substance. But upon looking at the characteristics of certain substances, they realize that, okay, earth is not as simple as they had thought. When studying earth, they realized that some components of earth were magnetic, some were not. Some components of earth could be ignited, some could not, right? So they realized that certain substances, where they figured, okay, an element is earth. Earth wasn't as simple as they realized. It was made up of even simpler substances. So that gave rise to things like sulfur, and them realizing that iron is a separate substance, and and things like that. And then realizing that, okay, what, well, through the years they realized that, okay, water is made up of different substances, and things like that. So upon studying these elements, and I'm using air quotes for elements there, upon studying these elements, um they realized that, okay, the things that we thought were the elements aren't actually the elements. So they discovered some other stuff. Now gradually, these men, I wouldn't call them scientists as yet, these alchemists, if you want to put term it like that, these alchemists, well, actually, yeah, they were scientists. I can't say they weren't scientists, but these alchemists became less and less interested in, just converting lead into gold, or converting or finding the philosopher's stone. They became less and less interested in that, and more interested in figuring out how other changes work, like how things eroded, how rusting occurs, how combustion works. So they became less and less interested in what they started out for in the first place, and more so on uh, figuring out these things that they were seeing now in everyday life. So yeah, so I know this class would have gotten a lot of references. So yes, so that was where it came to be, and gradually the field of alchemy, became more about that and less about finding the philosopher's stone. And so alchemy became what is known as modern chemistry. Someone asked me to allow someone to enter, but I'm not seeing them in the waiting room. So let them retry. Yeah.
So I see not seeing you, so you could retry.
Sorry, you mute yourself.
A smaller screen. Terrible. Yes, I'm forgetting that I'm not the host. Kamari, whoever's thing, just let them in, please. Thanks.
Yes, sir, I already did.
All right. Yeah. I was looking for admit and I'm not seeing anything. Anyway, yes. So yeah. So that's what went on, and so that's where we were at that time. Now there came a point in time when more and more elements were being discovered, and they were trying to figure out a way that we could list these elements, but that it made sense. Not just a randomized way of listing the elements, but to have some order about them. Now, at this point in time, they realized that okay, some elements have different masses, right? So, well, obviously, because some elements are denser than others, some are uh, have different mass ratios and things like that. So they knew of atomic masses. So they said, okay, let's arrange these elements according to their atomic masses. And so various scientists were going about their work around the same time. There was now came this scientist by the name of Mendeleev, working on the periodic table, and at the same time, around the same time, a little bit before, I believe, there was another scientist. I believe it was a Frenchman. I can't remember the name right now exactly. Um, you see, no matter how hard you try to do work, if you ain't get perfect, if you ain't get the results, people don't remember you. It shouldn't be like that. Anyway, so there was another scientist. I'll tell you his name another time. But both of them were working on the periodic table at the same time, and he was following what was originally the idea. Let's list these elements according to atomic mass, and that's what Mendeleev did in the first place. He arranged them according to mass, but then he realized that at every certain instances there was a repetition of uh, actually, sorry, he noticed a trend. He noticed trends in their character. Like when he was listing them according to atomic mass, he noticed certain trends. Like when he was listing, he noticed, okay, here's a metallic substance. Here's something that's less metallic. And as I'm listing it, it's getting less and less metallic all the way up to the most non-metallic things. And then all of a sudden, it starts becoming metallic again. And then the trend repeats itself. So he was noticing at the time, well, what we refer to now as a periodicity among the elements, right? Basically, he was seeing that there was a certain trend, but the trend didn't just continue just like that. Yeah, thank you for the name. Yeah, so Antoine something or the other. Yeah, so uh, he was listing them according to that. And so he said that, okay, as I'm listing them down, let me put the other row just below that, right? So it makes sense. I'm not just going to list them, but because I'm seeing this repeating trend, let me just put every trend in one row. And he did that. And so he realized again that as he was doing that, they were very similar elements together when looking at it from top to bottom. And we know that today as the groups, right? So he noticed that as he was putting down these elements, when he aligned them together, these elements from top to bottom were very, very similar to each other. Don't worry, you don't need to know how to pronounce it for now. You just need to know how to spell it, right? I didn't. Let me see. I didn't actually see the name too well just now. So, oh, Becquerel. Wow, if I'm pronouncing it correct, Becquerel.
I'm not even gonna try to pronounce that.
I think it's Becquerel.
I
You
think it's
can Google it
Becquerel.
for the
Becquerel,
pronunciation. It's on Google.
Google pronunciation.
I
Yes.
think
It
it's
sounds like
Becquerel.
Quirrell in Harry Potter. Anyway, so where was I? Yes. So it came to a point where he decided that okay, I'm no longer going to list them according to atomic mass. I'm going to list them based on the characteristics themselves. And he became so devoted to this new way of listing it that there came times when he had to shift around elements. Like for example, I believe it was with selenium and iodine, if I'm not mistaken, where they were actually the other way around because iodine is less lighter than selenium. And so he would have had iodine first and then selenium. But then he went with this according to his what he was seeing on the periodic table. He said that okay, iodine looks more like it fits on the other side, and selenium looks more like it fits on this side because of the elements at the top and bottom. So he made the switch without any at that time without any feasible reasoning. He made the switch, and so because of this, people weren't that people didn't like the idea of what he was doing. It seemed like it was just arbitrary, that it was just random, and so uh, they didn't really bother with his version of the periodic table at that time. Another thing that they were worried about was that he actually left spaces within his periodic table because he saw when he was fitting these elements, he saw that based on where these elements fitted, it there wasn't he ran out of elements to fit the spaces. Or it's like okay, he would see an element that would fit together in what we know now as group one, and then the next element that he was to put in would fit somewhere like group four. So he knew that, okay, if this element fits well in group one, he placed it there. And the next element fits well in group four, he placed it there instead of just putting it in group two. So he accommodated the characteristics and not just listing them in order. So that left gaps within his periodic table. What actually happened though, to make scientists accept his periodic tables after a while, in filling out these in leaving these gaps, he predicted what the characteristics, well, I mean, you would realize now how, right? But at that time it was kind of like a stretch. But um he predicted what the characteristics of those gaps would be. So he said that okay, if this element should be in this group, the second column in my periodic table, the characteristics would be X, Y, Z. The characteristic, I would assume he would say, okay, the characteristics would be it's slightly less, it's very metallic, but slightly less metallic than this other one here. It's it binds to halogens, or it combines with halogens in a 1:2 ratio, and so on, right? So he that was his reasoning for it. So he said that okay, I'm leaving a space in the or I'm leaving a few spaces in my periodic table, but I know the characteristics of the elements that would fit in those places. And so when the time came and a new element was discovered, it fit he was able to describe it perfectly. It fit his prediction of what the element would be like. And then another was discovered, and then another. So it's just a cover, don't worry. So so then is when scientists accepted his periodic table because it fit more in line with what was being discovered. And so that actually gave rise to what we use today um, in the periodic table. Eventually, they realized that instead of atomic mass, we should be using atomic number. which was what Mendeleev was doing, although he didn't know at the time that that's what he was doing. And so, yeah, that's basically a quick run through of how the periodic table as we know of it came into being. Now, if you could just finally go on to the next slide. Right. So this was what I was talking about. So as I said, he left spaces. He predicted the properties of the elements that weren't discovered at the time. But we know now that elements are arranged according to atomic number. So going down from top to bottom, we refer to those as groups, right? The vertical lines are referred to as columns. They refer well, vertical lines are columns. They're referred to as groups, and elements within the same groups have similar properties. You see highlighted there on the first periodic table there, you see highlighted in red is group 1. We refer to them as the alkali metals. And the other in blue is it's group 17, we refer to as the halogens, or well, basic group 7. I'll talk about that in a minute, just why we are 17 and why we are 7 and so on, right? And the rows are called periods, right? Now, periods are where you would see the trends from the start of the period to the end is where you would see the trends. The periods, all members in the same periods have the same number of shells, have the same number of energy levels, occupied energy levels. Next slide, please. So the periodic law is basically the principle of the modern periodic table, is where the elements are arranged according to atomic number. And well, they realize upon the use of Mendeleev's periodic table, they saw it come out. So yeah, that's it. I mean, it seems obvious to us now that, and it's actually a law, right? Next. So here you have a periodic table showing you various groups. We have the alkali metals, which is in blue. In white there, if I'm seeing correctly, are the alkaline earth metals. We have some non-metals in orange. We have the halogens, or the group 7, in green. We have the inert elements, or the noble gases, in pink. In is that a peach color? In peach, we have similar some metals that are not transition metals. We have the transition metals in period. Thank you, coral. Is that lilac or purple, whatever? It's a kind of purple, the transition metals. And looking like yellow, the rare earth metals. Now here is where I'll discuss this with you. Now you see, yeah, I'll talk about that in a minute. Now you see where the headings are. You see some Roman numerals there, right? That was the original numbering of the periodic table. Would be group 1, group 2, and then all the way over there where the orange is, you see group 3, group 4, and all of this is in Roman numeral 4, as in IV and V and VI and so on, up to the noble gases, and the noble gases would be group 8, right? Now, after that point in time, they use the transition metals. They give it another numbering scheme, So they had to differentiate it. So the original numbering became A, as in 1A, 2A, 3A, 4A, and so on. And the transition metals had 1B, 2B, 3B, 4B, 5B, and so on. And now with the new number system, they just use Arabic numbers, that's well, our numbers, and they just number 1, 2, 3, 4 straight across, including the transition metal. So Roman numeral 1 and Arabic 1 would be the same thing, would be the alkaline metals. Roman numeral 2 and Arabic 2 is the alkaline earth metals. 3 would be where the orange starts, whereas Arabic 3 would be where the transition metals start. So if you count the transition metals, there's actually 10 of them in a row. So Roman numeral 3 on the orange section is actually Arabic 13. So whenever we talk about group 13, that could be group 3, 3I, group 14 is group IV, group 15 is group V, and so on, right? So that's the only difference there with the other side of the periodic table, because although new convention uses Arabic 1, 2, 3, 4, 5, 6 up to 13, 14, 15, up to 17, we still use the Roman numerals for, because it's clearer when we use that, right? Also, however, now we don't really say group 8 or group 18. We say group 0 for the inert metals, because of course helium is also there, so you know, it doesn't make sense to call it 8. Now in terms of the blocks, right? Now how it's colored there, it's colored there to show you the different things, right? Like the non-metals in orange, the other metals in coral, the halogens in green, the inert elements in pink, whatever, right? But they're actually blocks. Now, the first two columns there on your left, that would be the alkaline metals and the alkaline earth metals. Those two columns there, that's a block by itself. We refer to that as the S block. Now, that square piece starting from, okay. Okay, the square piece starting, okay, let's end the meeting here and I'll restart. So everyone can join the same, I'll send the link, I'll send the link. Yeah, so Kumari, just please end the meeting.